research that's really changing not just our understanding of those areas, but certainly making great contributions to this country. So to me, if you look at the great things we're doing in NASA science right now, from studying the sun, trying to understand its behavior, and of course then how that impacts the Earth, from looking way back into the origins of the galaxies and of the universe, to how stars form, how planets form, how galaxies form, to the scope of the research that we do on the International Space Station, not just looking at certainly the behavior of things like how do materials behave differently in microgravity, how does combustion take place in microgravity, and how can we use that information to better understand those processes and maybe turn it into things that will benefit us here on Earth. But of course, we're also using the International Space Station as a platform to study the long-term effects of spaceflight on humans, because that's ultimately what we want to do. That's what we're here for. We want to get humans beyond low Earth orbit. We want to expand out into the solar system, and John and I want to see those geologists, astronomers, astrobiologists walking on the surface of Mars. Obviously, we've got Juno on its way to Jupiter, and if you look at the scope of spacecraft right now that we have across the solar system, it's truly impressive. And then also at this meeting, just a ton of research highlights about the Earth, all the observations we're making at the Earth, from understanding things like natural hazards to certainly our rapidly and worryingly changing climate. But if you think of those things, they all seem sort of like they were on that chart. Each of them is in their little separate areas. So I think part of my job is to try to articulate the connections between all the things that we do. And I really go back to these three basic questions that you see on this chart, that we see on so many sort of NASA fundamental documents. Are we alone? How did we get here? And how does our universe work? And you can really turn that back into saying that really a lot of what we do, whether it's studying the sun, whether it's looking out into the galaxy with Hubble, is really all about origins and evolutions. How did everything that we look at, that we see, including us, form, and how have we changed over time? If you think about the universe, the amazing things that are going on, and to me, since this is really not my field, I'm a planetary scientist by background, geologist, I do study the Earth. Trying to get up to speed on all of the things that we're doing in astrophysics is really just amazing. From, again, looking back at those earliest times of trying to understand what happened in those very earliest moments of the formation of the universe, looking at black holes at the centers of galaxies. What are they there? Why are they there? What are their characteristics? And of course, the endless search for dark matter. And part of what we're doing, using instruments like Hubble again, but Planck, our whole array of tools that we have had over the last 10 years, trying to understand this early stage of stars. And obviously, the James Webb Space Telescope, which we're incredibly excited about to be launched in 2018, is really going to turn everything we know on its head, just like Kepler has just done for understanding extrasolar planets. And this issue of the origin and workings of stars, not only do we want to understand it outside of our own solar system, because we certainly want to understand our own star, but then understanding other stars and how they form across the galaxy. For solar systems, we obviously have this wonderfully diverse solar system that for so long was what we knew and what we could study. We went from 9 planets to 8. I guess we went to 8, then 9, then back to 8. And we had so many ideas of how our solar system formed that I learned, when I was in graduate school back a large number of years ago, that sort of explained why you have giant planets out at the back of the solar system and all the rocky planets in the inner solar system. And that was sort of the canonical way that we understood, because we had an example of one. And to me, this very question, or this very issue is why we do planetary science. This is why we do astrophysics. This is why we do what we do. Because when you only have one example to study, you are often led down the wrong path. If we have one solar system to study, we can come up with all kinds of theories to explain how it is, why it is. But then all of a sudden, when you have many solar systems to study, when you have planets all over the galaxy, not just in ours, all of a sudden everything you know changes. It's not what you thought was wrong, but it was you were looking at the tail of the elephant. Now all of a sudden Kepler's given us a okay, I was going to say back end, the whole front end. That sounds better. So, all of a sudden Kepler has just blown away. We've gone from 8 planets to over 3,000. What an amazing set of resources for scientists to study over the next 5 years. Then we're going to have TESS. Then we're going to have JWST. So we're not just going to know where these planets are and have an idea of their size and mass. We're going to start looking at their atmospheres. And what we're going to learn is really, truly going to be amazing. And back to origins and evolutions, and I adore this image. I think it's the best image we have produced in, I don't know how long. It's really my favorite, because not only is it this amazingly beautiful image of Saturn and its rings, it shows this outer icy ring that Enceladus produces by spitting out ice particles at us all the time. And you can see Enceladus sitting right there. But of course it also looks back. Venus is in the picture, Mars is in the picture, and of course Earth is in the picture. And to me this captures so much of what we've done over the last 50 years, exploring our own solar system, trying to uncover these worlds that went from being these places we didn't know much about to places where we now have a good idea what they're made of, we have some good idea of what their atmospheres are, how those atmospheres work, how those surfaces work, how the interiors of those bodies work. So with this fleet of spacecraft that we have sent out across the solar system, we've made so much progress on that sort of origin and evolution question. And of course, again, this image of the pale blue dot sort of puts the Earth and us in perspective. And Carolyn Porco, when she first released this image back about a month ago at the Library of Congress at an event honoring Carl Sagan, gave a very eloquent tribute about how this image was a redo of the original pale blue dot image that Voyager took, that Carl had been so interested in having to give us that perspective of looking out from across the solar system back at our home planet. It's nice to show so many remote images because they're dramatic and that's so much of what we do, but what's truly exciting is we've gone to this new phase over the last 20 or 30 years where we have not just looked at planets remotely, but we've been getting down on their surfaces and trying to understand those detailed processes and really sampling the rocks to get a better understanding of how those surfaces have evolved. And this image was put together by Michael Malaska of JPL, showing how these planetary surfaces, and you can learn so much just from looking at a basic image of a planetary surface, from the moon to the Soviet image of those plated flows on Venus, to of course Mars, that we have now a large gallery of images of what the surface of Mars looks like, to those little rounded pebbles on Titan that we can understand have been worked by flowing liquids to get that nice rounded appearance, to of course the oceans of our own planet. Really being able to contrast on a very human scale the different geologic processes that shape the surfaces of all the planets. But I think the other one, the issue on origin and evolution that's really connecting across all of what we do at NASA is the issue of life. And to me this is such an exciting time because of all these years of research that we've done. We know what the targets are, we know where to go. Certainly curiosity in exploring the surface of Mars is really basic questions of where we think and evolved on Mars, Europa, about Enceladus, about Titan. The solar system to really get at this issue is has it evolved in even more, or as my friend David Grinspoon has even proposed, in the clouds of Venus. But NASA's not just working on life on other bodies, we're working on life here on Earth. From thinking about things like asteroid hazards and our NEOWISE that just is getting restarted to continue the survey of asteroids across that could be a potential threat to the Earth, to the work that's done on the space station in areas like developing new vaccines, to, of course, looking at our own changing planet, not just using the ISS as a platform, but using free-flying satellites as a platform. And, you know, I say to people, you know, especially when I give public talks, if all that doesn't convince you, if all the science, you know, just leaves you kind of cold, you know, we're out there actually doing things on an everyday basis that help people here on Earth, again, on a daily basis, from, again, developing vaccines based on research from the International Space Station, from the monitoring of hurricanes that we're doing from our many assets in orbit, let alone the aircraft observations we do, and of course the Global Hawk program, which has finished its second year this year, to the monitoring of the sun that we do and helping to try to understand the sun, to get a better understanding of space weather, to the monitoring we do that goes into understanding natural hazards. And of course, climate change, we are, you know, it's occurring. How are we going to understand it? How are we going to prepare? All of these things require data, and we are gathering the data from things like soil moisture to monitoring ice through things like Ice Bridge, all the instruments that we have, the MODIS instrument on the Terra satellite, looking at the ozone hole through the ozone monitoring instrument, to soil moisture, and this is a model, but of course coming up, and I'm sure John's going to talk about this, we have an incredible array of Earth satellites that are going to be launched this coming year, from things like SMAP, that's going to be looking at soil moisture, to the Global Precipitation Mission, a whole range of assets, again, all aimed at one thing. Are we making all the measurements we can to accurately be able to understand how our climate is changing and why it's changing? One of the things that I want to work on while I'm in this position is communication, and obviously this is something that all of you are interested in. And this started right away when I started this job, because I got a set of charts that was sort of, here are our science highlights, and there was one of the charts that I didn't understand. It's not from my field, but I didn't understand what it meant. Why it was important, so I called someone in and they explained it to me, you know, with finger puppets, and then I understood it. But I have found, especially when I have gone up talking to various stakeholders in NASA, that a lot of times scientists come and talk to them, and while they kind of know it's cool and they think they've heard something impressive, they really don't understand it. And so one of the things that I'm working on with Sarah DeWitt, who works with me, is this issue of science communication. How can we be helping scientists across NASA communicate more clearly what it is we do, but not just what it is we do. I find a lot of the times we forget the why, and we forget the so what. And that's important, because obviously we're spending taxpayer dollars. We have to make sure that we're talking to the people who are paying for us, not the least of which each other, in a way that's clear and understandable. And again, that kind of why and so what is one of the things I feel like we do the worst on a lot of times. But obviously everything we do at NASA, to some extent, is about the people. And it's not just, I have the big hat of the NASA community here, which means industry, academia, and people within NASA itself. We are doing innovative things. We are making amazing telescopes here on Earth that we're going to send into space to try to understand, you know, things from the atmospheres of planets with JWST. We send scientists. We have a crew that just left, is leaving today, that contains a bunch of NASA scientists that are heading out to pick up meteorites across Antarctica. We have astronauts every day up on the International Space Station who are doing experiments that are helping to further our understanding of plants in space, of humans in space. Again, all of these things, all this work that we're doing. And of course, I feel strongly that we inspire, from the Curiosity landing to the rocket launches that we've been able to watch recently on the East Coast. We provide inspiration for students and even grown-ups across the country. And I think a great example of that was this Cassini image that was compiled from July. And of course, you can see it mimics the one I just showed. And it was this same day where we asked everybody, NASA asked everybody to wave at Saturn. And this is a compilation of those things, because obviously NASA just isn't about looking out, it's also about looking inward, and it's about inspiring the people right here on Earth. So those are my comments, and I'm willing to take questions, chat, whatever.